Let's imagine the universe from the very beginning. Not the beginning of planets or stars, but the beginning of everything, the Big Bang. A moment so hot and dense that space itself had no shape. Everything that would ever exist was compressed into a point smaller than anything we can imagine. Then, in less than a second, the universe expanded. It cooled. Particles formed. Some survived, some didn't. Matter and antimatter collided everywhere, destroying almost all of each other. But not perfectly, for roughly every billion particles that annihilated together, one extra particle of matter survived. That tiny imbalance gave us everything. Every star, every planet, every galaxy, and everyone who has ever lived. So what would happen if, in that delicate moment, the imbalance was off by just one atom, just one less particle surviving that early chaos? At first, nothing noticeable would change. The Big Bang would still happen. Space would still expand. The laws of physics would still function exactly the same way. But the first few minutes after the Big Bang were incredibly sensitive. A small difference didn't stay small. It spread outward into larger and larger differences, shaping everything the universe would eventually become. As the young universe cooled, protons and neutrons began forming simple atomic nuclei, mostly hydrogen, some helium, a trace amount of lithium. These were the first atoms, the building blocks for everything else. Now imagine that one of them simply wasn't there. Maybe a random fluctuation stopped it from forming. Maybe it annihilated with its antimatter counterpart a little earlier. No matter the cause, the result is the same. The early universe has one fewer particle of matter. You might picture that missing atom floating alone forever. But that's not how the early universe worked. Matter wasn't evenly spread out. It clustered into regions of slightly higher or lower density. Gravity pulled the denser regions together over millions of years. These regions eventually became galaxies. If one atom was missing, then one region in the early universe becomes ever so slightly less dense. Not enough for telescopes to notice, not enough for physicists to detect, but enough to slightly change how gravity behaves there. Imagine two clouds of hydrogen gas drifting close together in the early universe. In our world, one of them might become slightly more massive and collapse into a star sooner. In the alternate universe, it takes a little longer, or maybe it never collapses at all, or maybe it collapses faster because the missing atom changed the chain of gravitational movements around it. These small timing differences lead to the first stars forming in slightly different locations. The first stars, called population III stars, were enormous, hundreds of times bigger than our sun. They lived fast and died young, exploding as supernovae that scattered heavy elements into space. Heavy elements are essential for rocky planets. You can't make an Earth without carbon, oxygen, silicon, and iron, all of which come from dying stars. So now the alternate universe diverges a bit more. One fewer first-generation star forms, or one forms slightly later, or one forms in a spot where, in our universe, nothing happened. This small shift changes how heavy elements are spread through the early galaxy. The effect is tiny, but it grows over time. By By the time the Milky Way starts to take shape, the distribution of metals is slightly different. Not dramatically. The galaxy still forms, stars still shine, gas still rotates around the center, but star-forming regions develop in slightly different patterns. Fast forward a few billion years, our sun forms inside a cloud of gas and dust enriched by earlier supernovae. The exact mix of elements in that cloud determined the kind of planets that could form. In the alternate universe, the cloud is nearly the same, but not perfectly. Maybe there's a tiny bit less carbon, maybe a little less iron. Maybe the cloud collapses slightly faster, maybe slightly slower. The sun still forms, but the planetary disk around it behaves differently, even if only by a small amount. Dust grains collide. They stick together. They form rocks, then boulders, then planetesimals. Eventually, these become planets. Small differences in composition and timing change how these collisions unfold. Earth may still form, but perhaps it's slightly smaller, or slightly larger, or forms in a slightly different orbit. A small shift in orbit means a small shift in temperature. A small shift in temperature shapes what the early atmosphere becomes, and that atmosphere shapes everything that comes next. Life is sensitive to these details. Too much heat and oceans evaporate. Too little and oceans freeze. In the alternate universe, maybe Earth ends up slightly warmer or slightly colder. Not enough to make it uninhabitable, but enough that life evolves differently. Maybe the first living molecules form a little earlier, maybe a little later. Maybe the first organisms rely on slightly different chemical pathways. These differences matter over long timescales. Evolution depends on millions of lucky steps. Small nudges early in Earth's history can lead to different branches later. Different species surviving, different species going extinct, different organisms rising to dominate ecosystems. Perhaps intelligence still emerges, but it may appear in a different form, a different species, on a different timeline. In some versions of this alternate universe, intelligent life emerges earlier than it did here. In others, it never appears at all, not because the universe is broken, but because the conditions that favored our kind of evolution shifted ever so slightly. One missing atom didn't destroy the universe. It simply nudged it in a different direction. A small nudge at the beginning becomes a large difference at the end. By this point, billions of years have passed. Galaxies have formed. Stars have lived and died. Planets have appeared around countless suns. In many ways, the alternate universe looks the same. If you could look at it from far away, nothing would seem unusual. But as we look closer, we start to see the effects of that early difference. In this universe, some regions of the galaxy have slightly different amounts of heavy elements. These elements are essential for forming planets like Earth. A little less carbon or silicon or iron means some solar systems form fewer rocky planets. Gas giants may be more common in some regions. Other regions may form nothing but smaller, barren worlds. Move forward again, somewhere on a world that plays the role Earth plays in our universe. Life begins. The key question now is, how different does this life become? life depends on chemistry. Chemistry depends on the environment, and the environment depends on everything that happened before. Maybe the planet has slightly less water, or slightly more. Maybe the atmosphere holds a little less nitrogen, or a little more carbon dioxide. These small differences determine how quickly life evolves. On this alternate Earth, microbial life appears. It spreads through oceans, adapts to different environments, and slowly becomes more complex. But the path is different. In our world, certain evolutionary pressures triggered moments like the rise of photosynthesis, the development of complex cells, or the Cambrian explosion. In the alternate universe, these events may happen earlier or later. They might be milder, they might be stronger. This leads to different organisms dominating at different times. Some versions of this alternate planet may never evolve large animals at all. It might remain a world of microbial mats and small creatures. A stable environment sometimes prevents major evolutionary leaps. Or maybe evolution moves faster. Perhaps multicellular life appears sooner, creating a wider variety of organisms over time. Now, let's consider intelligence. Intelligence is not guaranteed, even if complex life evolves. It depends on ecological pressures, competition, climate cycles, and a long chain of chance events. In the alternate universe, those conditions might not align. Intelligent life may never develop. The world might flourish with diverse species, none with the ability to build tools, language, or technology. But in another version, intelligence arises anyway in a different species. Perhaps not primates, but marine creatures, or insect-like organisms, or reptilian species. Whatever emerges, it thinks in ways different from us, sees the world differently, builds different tools, reaches different conclusions about the universe. Civilization, too, is not a certainty. A species can be intelligent without developing civilization. It needs stable energy sources, access to resources, and relative freedom from natural disasters. Small changes in the planet's makeup influence all of this. Volcanic activity, climate stability, metal availability, and the presence of large landmasses. Maybe the alternate Earth has fewer metal deposits, making technological development difficult. Or maybe natural disasters prevent long-term settlement. Or maybe the atmosphere is too unstable for fire-based technology to flourish. Even if a civilization does form, its path will diverge dramatically from ours. Their astronomy, philosophy, technology, and history all follow different trajectories, shaped by the earliest differences in cosmic formation. In this universe, humanity may not exist at all, or exists in a different form, or appears at a different time, or evolves on a completely different planet. The deeper message is straightforward. Intelligence is not the universe's goal. It is a product of specific conditions, conditions that arise only in narrow circumstances, circumstances that were created by the exact amount of matter the Big Bang produced. With one fewer atom, those circumstances shift slightly, enough that the entire chain of events changes shape. Zoom out now. Look at the alternate universe from a cosmic perspective. Galaxies still collide, stars still die, Planets still orbit. The universe still expands under the influence of dark energy. Over trillions of years, stars fade, matter thins out, and the cosmos continues toward its long-term fate. But the details, the small details that matter to us, are different. In this universe, maybe no species ever asks big questions about existence. Maybe thousands of species do. Maybe intelligence becomes more common because different regions form stars more efficiently, or less common because early star formation was disrupted. In our universe, we often wonder if intelligent life is rare. In the alternate universe, it might be rarer still, or more abundant. The entire cosmic landscape shifts based on that tiny initial difference. So what have we learned? When the universe begins with one missing atom, nothing breaks. Reality doesn't fall apart. Galaxies don't collapse. Physics does not unravel. Instead, the universe simply becomes a different version of itself. One that evolves along a slightly altered path. Star formation schedules, elemental distributions, planetary systems, climate cycles, and evolutionary histories all shift by small amounts that grow into large differences over time. In the end, one missing atom isn't about the atom. It's about how sensitive the early universe is to initial conditions. A small difference at the beginning becomes a major difference at the end. The alternate universe is still beautiful, still structured, still full of stars and planets and the potential for life. But it may not contain us or anything like us. And that is the quiet lesson of this thought experiment. We exist because the beginning allowed us to exist, not because we were guaranteed.